Alright, it's your favorite time of day, physics time. This time we will work through text problem 8-2 for lesson 20. If you haven't already, pause the video for a moment to get out a scrap piece of paper or a blank printout of the problem and then read the problem. Look for those embedded indicators that will help you pinpoint the type of problem you're about to solve. Now, so when I read the problem, I picked out the fact that we have a roller coaster with an initial velocity at height h. The problem describes several situations that clearly spell out that we have a work and a potential energy type of problem. So that will play into our first step. We've got potential energy and work. Alright, so we've read the problem, highlighted some important information. Next we have our drawing, which is already done for us, and our given information, which I've listed out right there. Next we need to make our assumptions. We have to assume there are no non-conservative forces at play. This is important because we expect all the gravitational potential energy is converted to kinetic energy at lower points. And we want all of that kinetic energy to be converted back to gravitational potential energy once we get back to the starting height at point A. If conservative forces were in play, then some of the energy would be converted to thermal energy. It would not be put back into our total mechanical energy. Alright, so the work done by non-conservative forces happen to be path dependent. If that statement is gobbledygook to you, then feel free to pause the video for a minute, check out checkpoint number 1 in chapter 8 on page 180, and take a look at what's going on there. Next we have our list of tasks. We have quite a few here, but the first 3 are to calculate the work done by the force due to gravity at points A, B, and C, which we have here, here, and here. Next, we're going to calculate the gravitational potential energy if the ground is set to be our reference height of 0 at points B and A. And then finally, part F, if our mass of 825 kilograms were to be 2 times that, then what would the results for A through E be with that change? Now we have our physics step. Based on our careful reading of the problem and our understanding of the gravitational force close to the surface of the Earth, I want you to write out the physics equations important to accomplishing our tasks. So go ahead and pause the video. Alright, you should have listed out the work done by a constant force, which is the work is equal to the force vector, constant force vector, dotted with the displacement vector. Remember, close to the surface of the Earth, the gravitational force is essentially constant. Our other equation is the gravitational potential energy equation. Remember that our variable h is the height above a 0 potential energy reference point. Usually we say the surface of the Earth is our 0 reference point. But we can make it whatever we want because it's only a reference line. Now who's ready to solve? I know I am. Last lesson we learned that work is only done by a force if the force vector has a component that is in the same direction as the displacement. So, what direction does our gravitational force point? Go ahead and pause and think about it. If you drew a free body diagram like I did, you'd remember that the gravitational force points in the negative y direction. So, well, it actually points towards the center of the Earth, but in our case it happens to be in the negative y direction, according to my axes. So the work done by a gravitational force is only non-zero when we have a displacement in the, you guessed it, y direction. So, for part A, we're looking at the work done by the gravitational force. Well, we'll have to have a displacement in the y direction in order to have a non-zero answer. So, do we have any displacement in the y direction for part A? You're right, we don't. We start at height h and we end at height h. We have displacement, but our force vector does not have a component in the direction of our displacement vector, where the displacement vector is only in the x direction. So, as I write this out, we have the work is equal to our constant force vector dotted with our displacement vector. But as we continue, our mg times, which is our magnitude here, we'll do that, times our displacement, which is some distance, but guess what? The angle between our vectors is 90 degrees. Let me show you. We have our car here, and we have a displacement in the x direction, and we have our weight force in the y direction. So the angle between those vectors is 90 degrees, and the cosine of 90 degrees is 0. So the gravitational force does 0 work from our starting point to our point to point A, because there is 0 displacement in the y direction. Alright, so on to part B. Part B asks us to calculate the work done by the gravitational force from our beginning point right here all the way to point B here. This time, we do have a displacement in the y direction, a total displacement in the y direction of h over 2. So as we do our formula here, work is equal to our force vector dotted with our displacement vector. Now, if we're only taking displacement in the y direction into consideration, then we have our weight force, the magnitude of our weight force, times our displacement, which is h over 2, times the cosine of the angle between our vectors. And like I said, we're only looking in the y direction. Where theta is equal to 0 degrees, because they are in the same direction. Then we have 1.70 times 10 to the 5th joules. Now that's 3 sig figs, because that's how many sig figs we have here, here, and here. So all the important elements in our given information all have 3 sig figs, so that's what our answer is going to be. And of course, work is measured in joules, because we're looking at the energy transferred from an object due to a force. Then part C, this is getting to be a little redundant, but we see that our displacement is now a integer value of h, cosine theta, where again, the angle between our vectors, if we're looking only in the y direction, is 0 degrees. And not surprisingly, we get double what we got for part B. Alright, part D, we are tasked with calculating the gravitational potential energy at points B, then A. And this is under the assumption that we have a reference line of 0 gravitational potential energy at point C, or at ground level. Remember, when we calculate our gravitational potential energy, this variable h right there is in reference to a change in height. It's not necessarily the height above the ground, it's the height above our 0 potential energy point. So if I wanted to, I could make the potential energy 0 point here at B. Well, anyway, moving along, looking at part D, we're looking at the gravitational potential energy at point B. So again, we have mg in our change in height from B to ground level is just h over 2. And we shouldn't see any shockers there. It is equal to 1.70 times 10 to the 5th joules. Alright, and then part E, we're looking at the gravitational potential energy at point A. Where our change in height is 1 full integer of h, or 42 meters. Just write it again. And again, not surprisingly, 3.4 times 10 to the 5th joules. Alright, so let's think about our answer here for part E. At point A, we have 3.4 times 10 to the 5th joules of gravitational potential energy. And how much work does the force due to gravity do to get the car from point A down to point C? It does the same amount of work as energy is stored in the gravitational force at that height. Now, if we had non-conservative forces at play, we would still see the same gravitational potential energy. We would still see the same amount of work done by the gravitational force. The thing that would be different, however, is how much of that potential energy that we have just calculated is directly converted to kinetic energy. If we lose energy due to thermal processes like friction along the way, then our speed at point C will be such that the translational kinetic energy will not be equal to our gravitational potential energy. We will have lost energy along the way due to heat. And finally, for part F, if we take a look at the equations that we've used so far, we've used our work done by our gravitational force is equal to F dot D, where displacement in the y direction is the direction of our displacement here, which is parallel to our gravitational force. So we have, did it again, mass times gravity, that is our gravitational force, our weight force, times, we'll say, the absolute value of delta y here. I put absolute value on there because our force vector and our displacement vector are pointing in the same direction. They're both pointing in the negative y direction. And so I have my positive weight force, even though it's pointing in the negative direction. And when I look at delta y, it's final minus initial, but because they're pointing in the same direction, I just want the positive value. Then we look at our gravitational potential energy, and that is mgh. Now, where h is the initial minus final, the positive change in height. Okay, so if we take a look at both of our equations that we've used here, we have a mass term and a mass term. Both of our work and gravitational potential energy equations have a directly proportional relationship to the mass. So if we double the mass, what is going to happen to our values for work and gravitational potential energy? That's right, they will double as well. So that's how we can save ourselves a lot of extra effort here by recognizing that relationship and just say that all the calculated values for parts A through E will double. Alright, so that's what I wrote here. Now, that concludes this problem. I chose to do text problem A-2 because it gave me a chance to talk about the differences between conservative forces and non-conservative forces and what effect that has on the problem. And it gave me a chance to talk about gravitational potential energy at different heights and the relationship to the work done by a constant force. So until next time, keep up the hard work on your suggested problems. It will pay off in the long run when it comes to WPR time and T time. I'll see you all in class.